Let A, M, and N be n by n matrices with entries from a field F. If M times A is the n by n identity matrix, we call M a left inverse of A. If A times N is the n by n identity matrix, then N is a right inverse of A. It turns out that left inverses are also right inverses, and vice versa. But this fact requires proof. For now, let us prove the following easier result. If M times A is the identity matrix, and A times N is the identity matrix, then M and N are the same. So here's the proof. Say we start with M times A equal to I, and multiply both sides by N. Using the associativity of matrix multiplication, I can rewrite this as M times A times N equal to N. And now, we know that A times N is the identity matrix, so I get M times I equal to N, and that gives me M equals N. So that's the end of the proof. So we're going to define the inverse matrix of A as follows. If B is a matrix such that B times A equals A times B equals to the identity matrix, then B is said to be an inverse matrix of A. And one can easily show that inverse matrices are unique. And so the inverse matrix of A is usually written as A superscript minus 1. Now we're going to look at a way to compute inverse matrices. So what you do is, say you're given an n by n matrix A, and you first form the matrix A extended by the columns of the identity matrix. And you transform this into a matrix in reduced row echelon form. If the final matrix has the following form, the first n columns give you the n by n identity matrix, then the last n columns will give you A inverse. So let's look at an example. This time I'm going to take a 2 by 2 matrix with complex entries. So we have to row reduce this matrix instead. So what we're going to do first is we're going to replace row 2 by 1/2 times row 2. And that will give me this matrix here. And then I'm going to replace row 1 with row 1 plus negative I times row 2. And this is the result. So as you see, the first two columns give me the 2 by 2 identity matrix. So these two columns will give me the inverse matrix of A. So I'm going to write down A inverse is equal to 1 minus half I, 0, half. And you can check that if you multiply this and the matrix A, you get the identity matrix. Before we end, let's look at one property of the inverse. Take two n by n matrices A and B, and suppose that the product AB is invertible. Then what is true is both A and B are invertible as well. And the inverse of the product is given by the inverse of B times the inverse of A. So this is actually not a typo. The inverse of B does come before the inverse of A. Now it's not too difficult to check that this is indeed an inverse, because if you multiply this on the left of AB, using associativity, you can rewrite this as this. And this whole thing inside becomes the identity matrix. So you're left with B inverse times identity, which is just B inverse, times B, and that is just the identity. And you can check the other product. And this again will give you the identity matrix. The thing that is not so obvious here is this implication. If you start with assuming the product is invertible, that both A and B are invertible. And this again requires proof. And see if you can come up with the proof yourself.